Welcome to this explainer. I am absolutely thrilled to have you here today. Get ready, because we're about to embark on an incredible journey through the very fabric of the cosmos. Today, we're going to explore one of the universe's most fundamental yet completely invisible forces, gravity. We'll start out way up in the vast expanses of space, looking at the stars and planets, and then we're going to bring all that knowledge right back down to Earth. Basically, this is your complete masterclass on the physics of gravitation, perfectly designed to make these massive concepts crystal clear. Now, I want you to just think about this for a second. We know that literally everything thrown up falls back down to Earth, right? Rain falls, a dropped apple falls. So why doesn't the moon just fall down? I mean, it's a massive rock suspended in the sky, completely under Earth's gravitational influence. There's no string holding it up. This is the exact kind of profound foundational question that ancient astronomers and brilliant physicists grappled with for centuries. And answering it, well, it requires us to build an entirely new framework of how the universe actually moves. To answer that question, we're going to follow 5 steps today. 1. Kepler's laws of motion. 2. Newton's law of gravitation. 3. Acceleration due to gravity. 4. Gravitational potential energy and escape. And finally 5. Earth satellites.
Okay, let's dive into this with step 1, Kepler's laws of motion, the observation.
Long before anyone knew why the planets moved, they had to figure out how they moved. Johannes Kepler actually spent decades analyzing raw, naked-eye planetary data collected by Tycho Brahe, and from that massive pile of numbers, he extracted 3 incredibly elegant descriptive laws. First up, the law of orbits. He completely shattered the old paradigm of perfect circles, proving planets actually move in stretched-out circles called ellipses, with the sun sitting off-center at a point called a focus. Second, the law of areas. He realized planets speed up when they get closer to the sun and slow down when they're further away, which means they sweep out equal areas of space in equal amounts of time. And third, the law of periods. This is a precise mathematical relationship showing that the further a planet is from the sun, well, the significantly longer its orbital year is going to be.
Now, what's really interesting about this is how surprisingly simple it is to visualize Kepler's profound discovery of the ellipse. An ellipse isn't just some random sloppy oval. It's a very specific mathematical curve. It's like a giant puzzle piece of the cosmos. If you just pin down 2 ends of a piece of string, and these represent your 2 foci, and use a pencil to pull the string taut, you can trace out a perfect ellipse. For the planets in our solar system, the sun sits right at one of those pinholes, one of those foci. The other focus? It's literally just empty space. Moving right along to step 2, Newton's law of gravitation, the mechanism. So Kepler beautifully described the geometry of the heavens, but Isaac Newton, he made one of the absolute greatest scientific leaps in human history by discovering the physical mechanism driving the whole shebang. He realized that the exact same invisible force making an apple fall from a tree is the exact same force keeping the moon tethered to the Earth and the planets tethered to the sun. And this brings us to the universal law of gravitation. Let's actually break down how this beautiful equation works. F is the gravitational force. It equals a constant, g, multiplied by the mass of the first object times the mass of the second object divided by the square of the distance between their centers. What this brilliantly tells us is that as the mass of either object increases, the force gets stronger. Simple enough, right? But because that distance r is squared in the denominator, if you move the objects just a little bit further apart, the gravitational force absolutely plummets. It's an inverse square law. Actually, let's address a really common misconception here. Think about the massive Earth and the much, much smaller moon. Because the Earth is so huge, you might instinctively think, well, obviously it pulls on the moon with a way stronger force than the moon pulls on the Earth. But look back at Newton's formula. Those 2 masses are multiplied together. The force is a mutual interaction. Therefore, the force the Earth exerts on the moon is perfectly exactly equal and opposite to the force the moon exerts on the Earth. No way, right? But it's true. The moon pulls on us just as hard as we pull on it, which, by the way, is exactly why we have ocean tides.
All right, step 3, acceleration due to gravity, the local reality. We've been exploring the vast macrocosmos, but how do we actually experience this universal force in our daily lives? To understand that, we need to contrast 2 very different mathematical concepts. The value of big G, that universal gravitational constant from Newton's formula we just looked at, is an unimaginably tiny number. We're talking 6.67 times 10 to the power of negative 11. It is so ridiculously small that the gravitational force between everyday objects, like, say, you and the computer screen you're looking at, is virtually 0.
But this constant is the same everywhere in the universe. It was famously first measured way back in 1798 by Henry Cavendish in this incredibly delicate experiment. He essentially weighed the Earth for the first time by calculating its mass based on this tiny constant.
Now contrast that tiny universal number with 9.8 meters per second squared. This is little g. So the crucial point is that little g is not a universal constant at all. It is the specific acceleration due to gravity that we feel locally, right here on the surface of the Earth. It's the direct result of plugging the Earth's massive weight and the Earth's specific radius into Newton's universal formula. So when you drop your keys, they accelerate toward the floor at 9.8 meters per second every single second.
But here is where it gets really fascinating. Because little g depends on your distance from the center of the Earth's mass, it actually changes depending on where you are. On the surface, it's at its absolute maximum. But if you were to climb a high mountain, moving further away from the Earth's center, gravity actually gets slightly weaker. And surprisingly, if you dig down into a super deep mine, gravity also gets weaker. Why is that? Because the mass of the Earth above your head starts pulling up on you, canceling out the pull from below. In fact, if you could travel to the exact center of the Earth, the pull from all directions would cancel out completely, and your local acceleration due to gravity would be exactly zero.
Which brings us to step 4, gravitational potential energy and escape, overcoming the mechanism.
So, we're essentially trapped in a giant gravity well on the surface of a massive sphere. This naturally shifts our focus over to energy. What does it actually take to fight against this inescapable universal pull? To answer that, we have to talk about gravitational potential energy. Now, this concept can be a bit counterintuitive at first. In physics, we define gravitational potential energy as a negative value. Why? Well, because we have to set the absolute zero point of gravitational energy at an infinite distance away, where the Earth's pull finally, truly drops to zero. So, as an object falls in from infinity toward the Earth, it loses potential energy, dipping below zero. To put it simply, to lift something up, to move it away from Earth, you have to do work and add positive energy into the system just to try and climb back up toward that zero point at infinity. Which leads us to a seriously thrilling rhetorical question. By applying the principle of the conservation of energy, could we throw an object upward so incredibly fast that its kinetic energy completely overcomes its negative potential energy? Basically, can we throw something so fast that it literally scales the walls of Earth's gravity well and never, ever comes back?
Well, the answer is absolutely yes, and the magic number is 11.2 kilometers per second. That right there is the escape speed from the surface of the Earth. If you launch a rocket at or above this incredible speed, it's going to carry enough kinetic energy to just coast away to infinity, never falling back down. Now, to put that into perspective, compare that to the Moon. Because the Moon is so much smaller and way less massive, its escape speed is only 2.3 kilometers per second. And this perfectly explains a massive mystery. It's exactly why the Moon has no atmosphere. Any gas molecules that form on the Moon easily get heated up by the sun, they reach speeds higher than 2.3 kilometers per second, and they simply boil off, escaping into space forever.
And finally, we arrive at step 5, Earth satellites, the application.
So, how do we take Kepler's geometry, Newton's physics, and our understanding of energy and actually apply them to put artificial satellites into orbit for things like telecom, weather tracking, and GPS? I mean, we know we don't always want things to escape to infinity, right? Sometimes we want them to stay close, but just not fall back down. Remember our very first question about why the Moon doesn't hit the Earth? Well, the solution is brilliant. First, a rocket doesn't just shoot straight up. It turns and provides extreme horizontal speed. Second, Earth's gravity is continually pulling that satellite downward. But third, because the satellite is moving sideways so incredibly fast, the arc of its fall perfectly matches the curvature of the Earth beneath it. The satellite is falling constantly, but it's moving sideways so fast that the ground literally curves away before it can ever hit it. An orbit is really just an endless, controlled freefall.
Which leaves us with a totally fascinating puzzle to ponder. If a satellite is just experiencing Earth's gravity, pulling it down into an endless fall, why do astronauts inside the International Space Station float around? People always say they're in zero gravity. But as we've explored today, gravity is definitely reaching them up there. It's literally what's keeping them in orbit. The incredible truth is that the astronauts are completely weightless because both they and the spaceship are in that exact same continuous state of free fall together. They are literally falling around the planet forever. But that leaves us with one final provocative question. If orbits are just this super delicate balance of falling downward and moving sideways, what happens when a satellite eventually starts losing that horizontal speed? I'll let you think about that the next time you look up at the night sky.